Hello everybody and welcome back to another episode of Science with Mr. Emond. Today we're going to be continuing on in our unit on enthalpy, and we're going to be actually solving enthalpy problems today using something called bond enthalpies or bond energies, which is the topic for the day. So we know that all compounds have either covalent or ionic bonds holding them together. And covalent bonds will actually break if they absorb enough energy to break those bonds. And so what we're going to be doing today is actually looking at this and using those bond energies to calculate our change in enthalpy. And so we have this definition here. The amount of energy that's required to break a chemical bond is known as the bond dissociation energy. And you're going to hear me saying bond dissociation energy a lot today. So one thing that we're going to have to use is this table that's going to have single bond enthalpies, bond dissociation enthalpies, and multiple bond dissociation energies. And you can find this on Schoology. Let's go ahead and show you where that is. All right, so here we are on the physical science homepage. We are currently in the unit on heat and we're in HT2 enthalpy. And you can see here there is a page called bond enthalpies. And when you open that, you will have all of these bond enthalpies that we'll be using today in our lesson. So make sure that when you're doing the practice questions, you are using these tables so that we all are using the same values and end up with the same answers. All right, let's go back to the smartboard. Okay, so let's learn a little bit more about bond energies. So bond energies can actually, these values that we're going to be using can be used to calculate the approximate enthalpy change, or our delta H. This is what we were doing in the previous lessons. Now we're just calculating our change in enthalpy in a different way. So we know that during a chemical reaction, the bonds in the reactants have to break. And to break those bonds, you actually have to add energy to them, which is, of course, an endothermic process. Then the bonds in the new products have to be formed. And to form those bonds, energy is going to be released, which is, of course, an exothermic process. And we can use this information that energy has to be absorbed in the reactants to break the bonds. And when you create new bonds, energy is going to be released to find the change in overall energy from before and after the reaction has taken place. And that, of course, is your change in enthalpy. So there we have what is going to begin our equation. So our delta H is going to be equal to the sum of the energies needed to be absorbed in order to break our old bonds. And this is always going to be a positive value. And the way that we're going to write this in math is the sum of the number of dissociation energies for each bond broken. And so if there are 3 carbon-hydrogen bonds, we're going to go to our table of values to find the energy, the dissociation energy. That's what DH is. DH is the dissociation energy. If a carbon-hydrogen bond has a dissociation energy of 314 kilojoules per mole, and in our reactants we're breaking 3 of them, then it would be 3 times 314. But most likely we're not just breaking CH bonds. There's probably a whole slew of other bonds that we're breaking. And so on this side, you're adding up all the bonds that you're going to be breaking in terms of their dissociation energies. And then you're going to subtract the sum of all the dissociation energies of the bonds that are being formed. And so this is the sum of energies being released when you form new bonds. And of course, those are going to be negative values, and we're forcing it to be a negative value through this subtraction sign here. Okay, let's go ahead and actually try one of these problems so you can see how how it works. So in example 1 here, we're using bond energies and a balanced chemical equation to estimate delta H. And we're going to do that for this word problem. Calculate the enthalpy change for the formation of propane gas. So we're forming propane gas, which is C3H8. And this is from the reaction of propene gas and hydrogen gas. And so over here we have our propene gas, C3H6, and hydrogen gas, which is of course H2. And the first thing that I recommend that you do when you solve any of these problems is draw out your compounds, okay? And so here I have drawn out my propene gas and my hydrogen gas and my propane gas. And now I'm going to look at what's actually going to happen here, okay? So the first thing I want to point out to you is, why don't you look at what I'm highlighting here in teal? We have this section here. Now over in propene gas, what do you notice about this section that I'm highlighting here? They are exactly the same. And so what's going to happen is, we're not just going to randomly start breaking all the bonds. These bonds here that are highlighted in teal do not need to be broken because they're going to be reused on this other side. Look at this in dark green here. We have 2 carbon-hydrogen bonds on the left and on the right. So of course we're not going to break those either. What do need to get broken? Well, I already kind of had them highlighted, right? This carbon-carbon double bond has to be broken. It doesn't exist on the right-hand side. And this hydrogen-hydrogen bond has to be broken. It doesn't exist on the right-hand side. And what needs to be formed? Well, we need 1 carbon-carbon single bond and 2 carbon-hydrogen single bonds. And so, let's write this out. So, we are going to need to break 1 carbon-carbon double bond. And let's look at our table of values. When we look at our table of values, we can see that a carbon-carbon double bond has a dissociation energy of 614 kilojoules per mole. And that's the only thing we're going to have to break in our propane gas. We also need to break 1 hydrogen-hydrogen bond. And so let's go ahead and do that. Well, each hydrogen-hydrogen single bond has a bond dissociation energy of 436 kilojoules per mole. And what are we going to have to form? We're going to have to form 1 carbon-carbon single bond, which has a bond dissociation energy of 346 kilojoules per mole. And we have 2 carbon-hydrogen bonds that need to be formed, each of them having a bond dissociation energy of 414 kilojoules per mole. And of course, if you're wondering where I'm getting these bond dissociation energies, when you see me looking to the right, I'm looking at Schoology at those table of values. And that's what you're going to be doing when you work on your practice problems in a second. So now we know all the bonds that need to be formed and broken, and so we can start to create our delta H expression. And so delta H is going to be equal to the sum of the bonds that need to be broken. So that's 1 carbon-carbon double bond, which is 614 kilojoules per mole, and 1 hydrogen-hydrogen double bond, which of course is 436 kilojoules per mole. And that's it for breaking bonds. Now, what bonds need to be formed? Well, we're subtracting. And we have 1 carbon-carbon single bond. And we have 2 carbon-hydrogen single bonds. There we go. And now we can simplify this. So we have delta H equals, I'm going to go to the calculator now, and we want to do 614 plus 436, because there's only one of each of them. So this is going to be 1050 kilojoules per mole, and we're going to want to subtract 346 plus 2 times 414, which is 1174. Okay, now let's actually do that. So our delta H is going to be what? Our delta H is going to be 1050 minus 1174 is negative 124. Negative 124 kilojoules per mole. And so this is an exothermic reaction. It's a very small exothermic reaction. Not very much energy is actually being released. And so that's how you do these problems. Let's go ahead and have you try one. So let's do this one. So of course, again, we're using bond energies and a balanced chemical equation to estimate delta H. And what you're going to be trying out on this one is calculating delta H for the reaction in which hydrogen gas, which I'm telling you is HF, is being combined with fluorine gas, which I'm telling you is F2, in order to produce hydrogen fluoride gas, which is HF. Go ahead and try this out. Make sure you draw your compounds with Lewis dot structures. Identify what bonds need to be broken and what bonds need to be formed, and do not use bonds that are on both sides. If you don't need to break them because you need them on the right-hand side, then don't break them down. And then, of course, use your delta H expression and solve. We'll see you when you're done. Okay, welcome back. Let's go through the solutions. So you should have started off by writing out your equation. Hydrogen gas plus fluoride gas is going to create 2 moles of hydrogen fluoride gas. And so what do we have here? Well, we have one hydrogen-hydrogen bond that needs to be broken. We have one fluorine-fluorine bond that needs to be broken. And we have 2 hydrogen-fluorine bonds that need to be created. And so now we can use this information in order to create our delta H expression. And so our delta H is going to be equal to the sum of the reactant bonds that need to be broken. So there's one HH bond, which has a bond dissociation energy of 436 kilojoules per mole. Again, these are just from our table of values that you can find on Schoology. And there's one bond of FF, which has a bond dissociation energy of 159 kilojoules per mole. In the next step, we're going to be adding those two together. So 436 plus 159. Okay. On the product side, we have 2 bonds that need to be formed. And so these bonds, these HF bonds, have a bond dissociation energy of 256 kilojoules. And of course, 2 times 567, if you look in the calculator, is 1134 kilojoules. So that's 1134 kilojoules per mole. Now you're just going to start to add them together, right? So 436 plus 159 is equal to 595 kilojoules. And we need to subtract 1134 kilojoules per mole from the bonds that are being formed. And so when you do this, you get a delta H of negative 539 kilojoules per mole. Okay, let's move on. All right, let's give this one a shot. So you're being asked to use your bond energies and the balanced equation to estimate delta H, just like we did in the previous problem. And we're calculating the enthalpy change for the reaction in which methane, which is CH4, is combined with chlorine gas, so that's Cl2, and fluorine gas, so that's F2, because these are both diatomic molecules, to produce Freon 12 gas, which is CF2Cl2. And there's some byproducts here that are not stated in the equation. That's why I've given this equation to you. And the byproducts are hydrogen fluoride gas and hydrogen chloride gas. And of course, then you'd have to balance it. So one thing that you should be doing, especially on level 4 questions, is making sure that it is balanced. In this case, I'm providing a balanced equation for you. And so what I want you to try is to use this balanced equation in order to do your calculations to find delta H. Go ahead and give this a shot and come back when you think you have the solution. See you soon. Okay, welcome back. Let's take a look at the solution. So the first thing that I would recommend doing, which hopefully you did, is to draw out your molecules. So here is my methane, which has 4 CH bonds. And so I wrote here 4 CH bonds. And I also wrote down each CH bond is actually 414 kilojoules per mole. Then I have 2 chlorine gases. And so a chlorine-chlorine bond looks like this. And I have 2 of them. So I have 2 chlorine-chlorine bonds, each of which has a bond dissociation energy of 242 kilojoules per mole. Then I have 2 fluorine gases. And so that means I have 2 fluorine-fluorine bonds. And each has a dissociation energy of 159 kilojoules per mole. Then I have my complicated molecule here, my Freon 12 gas. And I can see here when I draw it out how it would look. And that means that I have 2 carbon-fluorine bonds that have dissociation energies of 492 kilojoules per mole. And I also have 2 carbon-chlorine bonds that have dissociation energies of 324 kilojoules per mole. And then finally, for these last 2, I have 2 hydrogen fluoride gas compounds. So there's 2 hydrogen fluoride bonds, each with 567 kilojoule per mole dissociation energies. And I have 2 hydrogen chloride gas molecules, so that means 2 HCl bonds with bond dissociation energies of 431 kilojoules per mole. Now, this information is going to be used to be plugged into your delta H equation. And so your delta H equation is going to be the sum of your energies required to break bonds. So that's on your reactant side. And so we're breaking 4 CH bonds with that 414, 2 ClCl2s with that 242, and 2 FF bonds with that 159. And these are going to be added together. Then we need to subtract the sum of our bonds being formed, so on our product side. And of course, there's 2 CF bonds with 492 each. There's 2 CCl bonds with 324 each. There's 2 HF bonds with 567 each, and there's 2 HCl bonds with 431 each. When you sum them together, and you can see how that's done in the calculator here, on your reactant side, you're going to have 2,458 kilojoules per mole, and on the product side, you're going to have 3,628 kilojoules per mole. And then, of course, you just subtract the product side from the reactant side to find a delta H of negative 1,170 kilojoules per mole. All right, let's move on. Okay, so this is going to be the last problem of the day. What we're going to do is we're going to estimate delta H using our bond enthalpies, and we're also going to determine whether it's exothermic or endothermic. And what are we looking at? We're looking at the complete combustion of ethane gas. So hopefully you remember what ethane gas is from our organic chemistry unit that we did. But if you don't, ethane gas is a 2-carbon compound with the carbons being triple bonded. So go ahead and combust that and work out your solution. And when you're done, come back and I'll have the solution ready for you. See you soon. Okay, welcome back. Let's go through the solution. So the first thing to do is to write out your equation. So you would have started with ethane gas plus oxygen gas, because it's combusting, is going to turn into CO2 and H2O, because those are the products of combustion. And then you would have balanced it, right? So balanced it with the 2, the 5, the 4, and the 2. But then you would have realized, okay, well, that's my balanced equation, but there's only supposed to be one ethine, because I'm only combusting 1 mole of ethine in my reaction. So you would have to reduce everything. So divide everything by 2 to get you C2H2 plus 5 over 2 O2 turns into 2 CO2 plus 1 H2O. And this is the reaction that we're going to be using, the mole to mole ratios, because we're only burning 1 ethine gas here. And of course, the next step is to look at C2H2 and draw it out. So there's your C2H2. And you would then see that there's some carbon-hydrogen bonds. There's 2 of them per mole. And we have 2 moles of them. So how many are 1 mole of them? So how many bonds? There's 2. And each of those bonds has 414 kilojoules per mole of dissociation energy. And of course, there's 1 triple carbon bond with a dissociation energy of 839 kilojoules per mole. Now we have an O2. So here's the drawing of O2. And of course, there's 1 double bond per, and we have 5 over 2 of them. And so we have 5 over 2 oxygen double bonds, each with 498 kilojoules per mole. Now we have our drawing for CO2, and we can see here that what we're dealing with is oxygen-carbon double bonds. And there's 2 per, and we have 2 of them. So that means there's 4 of these oxygen-carbon double bonds, each with a dissociation energy of 804. And then we have water. So here's our water. This is water vapor, but water. And so we can see we have oxygen-hydrogen bonds, and there's 2 of them per, and there's 1 of them. So there's 2 OH bonds with a 463 kilojoules per mole bond dissociation energy. So now you're going to use those numbers to create your equation for calculating your delta H. And so we need to do our reactants first. So we're breaking the bonds first. There's 2 CH bonds. There's 1 triple carbon bond. There's 5 over 2 double bonded oxygens. And then we're going to subtract our bonds that we're forming. And so we're forming 4 carbon oxygen double bonds and 2 oxygen hydrogen double bonds. Now, of course, you can see in the calculator there, when you add them together, you get 2912 kilojoules per mole minus 4142 kilojoules per mole, and that is a delta H of negative 1230 kilojoules per mole. Is that endothermic or exothermic? That is exothermic. And of course, we should have known that because we're burning something. And when you burn something, when you combust something, it's going to release heat. So our delta H should definitely be negative. That's it for the day. Hopefully you enjoyed this lesson. See you next time for more on enthalpy. Bye-bye. Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end. And over here, you will find the next video in this unit. Keep learning, everybody. Take care.